Floor is yours. Thank you.
Excellent, thank you. Good afternoon, everybody, and good morning to myself. We are 3 hours apart right now, so it's just 10 here. And thank you for inviting me to speak today. And I'll talk to you about discrete carbon nanotube dispersions to enhance performance of additive manufacturing materials. I'll introduce a little bit McNano. We are a startup located in Mesa, Arizona, and we are focusing on improvement of additive manufacturing materials performance through nanoengineering. We specialize in nanomaterial preparation, functionalization, and their dispersions. Technology development on a carbon nanotube focus started around 10 years ago with our partners, and back in 2018 we started to focus in that technology specifically for additive manufacturing. In 2020 we went into commercialization stage to developing our first product lines, and back in 2021 we came out from so-called stealth mode and got ourselves known to additive manufacturing community as one of the players. So as I said, focus is nano-engineered materials. Nanoengineering is a branch of engineering that deals with nanomaterials and how they interact to make them useful and create different materials, structures, devices, and systems using nanomaterials. What is nanomaterial? Nanomaterial is any material of which one dimension is a nanoscale, which is from 1 nanometer to 100 nanometers. They could be dimensionless, which means all 3 dimensions are nanoscale, such as nanoparticles and quantum dots. One-dimensional nanomaterials is 1 dimension in a macro scale and 2 in nanoscale, which is nanorods, carbon nanotubes, etc. 2-dimensional materials, 2 dimensions are macro scale and 1 in nano, which is graphene sheets, films, coatings, or self-assembled monolayers, and also 3-dimensional nanomaterials. It's mainly bulk powders of nanomaterials or dispersions of nanoparticles in different solutions and multi-layer structures. So what is so great in nanomaterials? A lot of you might be aware they possess unique properties, but where the properties are coming from? Nanomaterials have large surface area to volume ratio. Imagine a cube with volume 1 for simplicity. Surface area of that cube is 6. It has 6 sides. Now split that cube in 8 smaller cubes. Your surface area becomes 12, while volume keeps constant, 1. Keep splitting it down and shredding it into smaller pieces, surface area becomes 24, and so forth and so on. So that surface area to volume ratio changes exponentially with decrease of the size of those particles, which leads to a massive amount of surface atoms on the surface. That, in effect, changes mechanical, optical, catalytic, and other properties of the material. Size matters. Don't believe anybody who says it doesn't, especially when we talk about nanomaterials. For example, plot on the left shows decrease of melting temperature for the gold nanoparticles as you shrink in the size of particle from 20 nanometers to approximately 1 nanometer. It changes exponentially. So you don't need to provide that much energy to melt gold anymore when it's shrunk down to nanoscale. One of the best and my favorite examples of nanomaterial properties as a function of size, it's quantum dots. That is on a graph on the right side. You're right as well, because you're looking at the screens. I always have to be aware of that. So that is example. Quantum dots have unique fluorescent signatures. So when you interrogate it with UV light, they fluoresce at different wavelengths. In this case, it's cadmium selenide quantum dots, and they pretty much, their fluorescent signature covers almost the entire visible spectrum. What is amazing about it, that the particle size changed on this plot specifically just from 2 to 6 nanometers. And it covers the entire spectrum. They also glow very beautiful, colorful, all the rainbow colors when you interrogate it with UV light, which is pretty amazing and very cool to work with them. There is a lot of nanomaterials out there, commercially available, synthesized in a lab, in R&D groups, national labs. And as I mentioned before, you can classify them by the dimensionality, but also you can classify them by different compositions. They could be single constituent, like on previous slide, gold nanoparticles, for example, composites, which is 2 or more components in a nanomaterial, like cadmium selenide quantum dots. They could be made from inorganic material, carbonaceous, metallic, ceramic, etc., or organic, such as polymers, dendrimers, nanogels. You also can classify them by morphology, based on their flatness, like graphene sheet. Picture that is shown down below, sphericity for buckyballs or nanoparticles, or aspect ratio, such as carbon nanotubes and nanorods, how long they are, what is their diameter. You can also classify them by state, which is isomeric, inhomogeneous, whether they're dispersed or they're agglomerated. So there is numerous amount of nanomaterials out there, numerous classifications. There are a lot of choices to pick from. Here's a few examples on morphology classification. I don't know, can you see the little mouse over? I hope you do. If you don't,
yes.
Here's the image here. On the left side is cadmium selenide quantum dots, 2 nanometers, which is, they're all spherical, quite uniform in their size. In the middle, it's SEM image of a gold nanorod surrounded by spherical particles as well. And SEM image on the right shows gold nanonetwork that formed on an electrode surface. As you see, there is a lot of variety of nanomaterials out there. Unique properties led to various industrial applications of those materials, with leading in electronics industry that uses it for sensors, integrated circuits, lasers, LEDs, you name it. A lot of nanomaterials are used in those products, in your cell phones, for example, that you carry with you every single day. The next runners-up are medicine and cosmetics. It's from tissue engineering to pharmaceuticals, dentistry, skincare, makeup. The best examples are sunscreen that use titanium dioxide. On any cream that has SPF on it, uses titanium dioxide particles for protecting from sun. Some personal care items, for example, lateral flow strips, well-known pregnancy test, for example, used gold nanoparticles to form that desired or not so desired line that you're looking for. A lot is in renewable energies, which is solar cells, batteries, fuel cells, and many, many other industries. So they're very well versed in their properties and their application potential. We at McNano is a nano engineering company. Our current focus mainly on carbon nanotubes. We do have projects on other nanomaterials, but we're not going to talk about them today. What is carbon nanotube? It's a nano structure in a tubular shape, that's why it's a tube, with a wall thickness of just 1 atom, and it's composed typically of pure carbon. Their diameter is 10,000 times smaller compared to human hair, so it's around 10 nanometers. They were discovered back in 1991 and hailed the next revolution in material science. Why? Because they possess unique properties. For example, compared to steel, they're 100 times higher in tensile strength and thermal conductivity. They're also 6 times lighter and have 5 times higher modulus. Compared to copper, they possess much higher electrical conductivity, thermal conductivity, and current capacity. All these unique properties are seen as we're going to do a lot of amazing things and fascinating developments with carbon nanotubes, such as carbon nanotube bulletproof vests, very light airplanes, even elevator to space. Google it, carbon nanotube elevator to space. It was a project. However, it's been 30 years. We don't see the elevator to space, no carbon nanotube bulletproof vests. Why? There is a technical challenge when we work with carbon nanotubes. During their manufacturing process, they clump together into bundles that are extremely difficult to untangle. And it makes it very challenging to disperse uniformly. And if you do successfully, as I mentioned before, any nanomaterial has a lot of surface atom, which means very high surface energy. And when they're all in the same solution, the only thing they want to do is to join together and party to minimize that energy and go back into bulk state and agglomerate. Same true for carbon nanotubes. It's very hard to keep them apart. They like each other. Look at this image. This is a SEM image of carbon nanotubes as synthesized. A lot of bundles, a lot of clumps. Now look at it when it's zoomed out. The struggle of separating those tubes is real. It's really, really hard. It's billions, sometimes billions of tubes clumped together. And when you add that clumped tubes into any matrix material of interest, it often leads to degradation in the chemical properties because they generate stress points, they generate defects. And it's true not only for additive manufacturing, but any other composite manufacturing based on those materials. We at McNano work, as we call it, discrete carbon nanotubes. Our technology name is McT because we just were lazy to say Mac nanotechnology every single time we talk about it, so it's McT. What we do, we take tangled and impractical tubes and we make them discrete and functional. What it does, it provides a path to nano-engineer a wide variety of material properties into current additive manufacturing materials. You're not dealing with tangles anymore. You're dealing with discrete carbon nanotubes that you can leverage the unique mechanical or electrical performance, and I will show you some examples later. Material development stages typically include carbon nanotube sourcing, their detanglement, dispersion in a matrix material, and then customer integration to the additive manufacturing equipment and machines. We'll be talking mostly about these two, detanglement and dispersions. We'll see some example of parts, obviously. Detanglement includes mainly surface chemistry optimization of those carbon nanotubes. Dispersion, it's integration into matrix material of those nano-engineered tubes. The surface chemistry optimization, when you synthesize carbon nanotubes, it's pure carbon. It's not really good to disperse, clump, a lot of problems. So first thing we do, we oxidize those tubes. It's typically highly concentrated acid and high temperature. You undergo oxidation process, and the reason for that is to introduce carboxylic and hydroxylic groups to the surface of the sidewalls on the tubes. Those groups are great from the chemistry perspective. I'm a PhD chemist, so that's my kind of gig. Carboxylic and hydroxylic group are highly reactive, and there are massive amount of chemical reactions that you can introduce those groups to and attach different, as we call it, functional agents, such as amine groups, ester groups, thiol groups, and silane groups as an example. What is important here, that functionalization of the tubes is really a basis for surface chemistry optimization, which leads to optimal interaction to material matrix of the interest, and thus affects quality of dispersion. Matching carbon nanotube surface thermodynamics is the most important. That's why functionalization step is vital when you work with carbon nanotubes. Optical image on the left shows carbon nanotube dispersion in one of the binders for binder jetting, and it's unstable dispersion, as we call it. You see a lot of agglomerated tubes all over your slide on a microscope. Microscopy image on the right shows stable dispersion, and you probably won't believe me, but it's true. It's exactly the same concentration of carbon nanotubes in both. So that stable dispersion, what it means, we separated the tubes and we keep them apart, they don't agglomerate, you actually barely see them under microscope. It's just all gray background because of tubes. And that dispersion is very stable. It's on my shelf here in the lab for over a year. There is no tubes at the bottom. It's everything dispersed in a binder. No problems. And what it does, it allows us to integrate those carbon nanotubes into a variety of matrix materials. We were very successful in introducing them in epoxies, acrylic, polybutadienes, which is rubbers, and different salts for additive manufacturing. We also started to use this technology for powder coating for laser sintering. We can not only coat the powders with very uniform layer of carbon nanotubes, we also can control the layer thickness. Where it leads us to different processes of additive manufacturing and what kind of property benefits we can gain out of it. We demonstrated the technology for watt photopolymerization. That was our first. We also demonstrated it for material jetting, such as polyjet processes. We currently work on a project in binder jetting, laser powder bed fusion for polymers, and fused filament fabrication with our partners. And what we're looking for is enhancement in mechanical performance, electrical conductivity, thermal, magnetic. For that, we will have to modify the carbon nanotubes because carbon is not magnetic on its own. Also chemical and optical properties. And here I'll give you a few examples. For example, fracture toughness. Fracture toughness is material's resistance to crack propagation. Conventional fracture mechanics assumes a single dominant crack that grows in a self-similar fashion, which means the crack increases in size, but its shape and orientation remain the same. Here are different failure mechanisms. This is the notch. It's not a crack. It's typically done on the notched specimens. And there are different fracture mechanisms that could be present in a fiber reinforced composite. Number one is fiber pullout. When your fiber is not functionalized properly and not bonded to the matrix material, when you start pulling it, what happens? It goes like glove off of your fiber. Second mechanism is obviously preferred, is fiber bridging, which means fiber is going to hold that crack together and you will need to put more energy or force into breaking your specimen. Number three is fiber or matrix debonding, which means you created the bond between fiber and your matrix material, but it's not strong enough, so it starts delaminating from the fiber. Number four is fiber failure, which is interesting because typically polymers, not as strong as fibers, but you might be having really bad fibers in there if fiber failure happens earlier than the polymer failure. And matrix cracking. So that matrix cracking is very important because initial scale of failure in any composites in a sub-micron scale. And the goal of addition of nanomaterials is to control the failure on that scale specifically. And here's the good, well, this is not example, this is schematic of so-called fiber avoidance model. Why fibers are actually good for your composites. First, what happens, again, crack is typically a notch. And what happens that those isolated yield zone, or craze crack as it's called, forms ahead of the main crack that goes in the middle here. And they coalesce around the major fibers and fiber groupings. This is just schematic. The best thing is here, and I apologize for the quality because it's the best image I could possibly find from the literature. Here's the notch. And here's the crack starts forming. Those are on a glass fibered polymers. Those are glass fiber introduced in a polymer matrix. Your crack forms and it goes. And it hits the fiber. It has to go elsewhere. Okay? And what it does, it goes down and starts avoiding every single fiber. Hence, it takes longer for crack to propagate. Hence, it takes more energy to actually fracture the specimen. And here is the example on bisphenol F epoxy control and one that was modified with nano-engineered carbon nanotubes. Those experiments were performed at a different temperature, and both control experiment and nanotube modified resin went through brittle, ductile to brittle transition and then into ductile region at 60 degrees C. at all instances and all temperatures, carbon nanotube reinforced epoxy exhibited higher K1C values, which is a fracture toughness value. This experiment is done on a single-edge notched beam specimen, ASNB, according to ASTM 1820. And it's pretty much like 3-point bending test on a notched specimen that is performed at different temperatures. We're going further. We did the ramp test, which is done on 3 millimeter thick bars. It's a tensile test, but it's done at very slow speeds until fracture occurs at room temperature. Here's the notch. The first thing that forms is fracture initiation site, or pop-in. Notice how much that site is suppressed in a resin that is modified with carbon nanotubes. It's much smaller. The next region here is a microcrack zone. Again, it's much longer region for epoxy modified with carbon nanotubes and much shorter for just control epoxy. Also, microcracks seem to be much larger in the control rather than the modified resin. The next region is fast crack. It's when the force exceeded the limit and finally a specimen just cracks and breaks. In any instance, the strong suppression of crack initiation and propagation is observed in a nanotube composites compared to base epoxy, and K1C values are higher as well. It means you need to put more energy to break the specimen. We went a little bit further and we did fatigue lifetime enhancement experiment. We did it in a tensile bars. You put them in a tension at 80% of your tensile strength, then relax, and then do it again and again and again until rupture occurs. Bisphenol F epoxy, 3 specimens were tested, broke after 14 to 4,000 cycles. Nanotube modified epoxy survived from 12,000 to 17,000 cycles with no break on any of them. The reason we didn't conduct the experiment further because we were using university's instrument, and professor kicked us out because we occupied machine for too long and they needed to conduct their own experiments. So we halted the experiments after 12,000 to 17,000 cycles, and we never actually reached the fracture. Let's talk a little bit about wet photopolymerization. This experiment was done on off-the-shelf rubbery or flexible resin that we modified with carbon nanotubes and then compared the results with the control off-the-shelf resin. Ultimate tensile strength increase, elongation and break increase, but what was surprisingly is number of fatigue cycles. Again, it went from 4 to 39, which is 875% increase in fatigue lifetime, which is quite impressive for wet photopolymerization resin. Everybody is looking for engineered materials. Everybody is looking for materials that will outperform current material options. A lot of people ask us, okay, you put it in a vat, can you actually jet them? Carbon nanotubes could be very long, 100 micrometers or longer, while diameter is small. Nozzles on material jetting machine like PolyJet, it's approximately 70 micrometers. So can you actually jet? Can it be useful for material jetting or binder jetting or any technology that uses inkjet printheads? The answer is yes, we can. Here we're going to look only at the control green specimen and carbon nanotubes green, because post-curing protocols were not aligned well. There are different post-cures. But in any case, you see increase in tensile strength on the green specimens, increase in elongation and break, and again, impressive increase in fatigue life cycles, especially when you start post-curing. That 400 cycle is again didn't break. Again, when you post-cure too much, you might be reached the point you over-curing and starting aging your specimen, fatigue lifetime cycles drop. So would happen the same for the control experiment as well. Quite impressive results very first jetting experiments with carbon nanotubes on PolyJet machines. Let's talk about acrylates. A lot of people use acrylic resin. This is an example of rigid formulation. Formula One, it's our product line. It wasn't when we were doing experiments, so it became one later, and I will explain how and why. But we took a reference formula from one of our collaborators for the clear rigid formulation, and we modified with carbon nanotubes. We saw improvement in tensile strengths, yield strengths increased, tensile modules increased, which means specimens become more rigid, hence elongation and break dropped. Flexural strengths, we can't really compare, it's still TBD, as I would say, hot off the press kind of results. We're still waiting on the control on the flexural, but impressive improvement in impact resistance, 62%. On the rigid resins, it's pretty impressive. They typically very brittle. We are pretty much flash on the heat deflection temperature and a little bit higher. Well, 170% is not a little bit higher, but higher on the water absorption, but still below 1%, which is acceptable for what? For the polymerization methods. Additional benefits of adding quantum dots. Oh, carbon nanotubes, sorry, messed up the nanomaterials. It's magnetism. For that, as I mentioned before, we have to modify the carbon nanotubes with something magnetic. And we did. It could be useful in processes such as 4D printing. A lot of people focuses on that, is printing shape memory alloys and anything that will react to the external stimuli after you fabricate your parts. We just went wild. We like making small videos. But think about adding this powder into any flexible resin and you can generate some actuating parts, right? When you put magnetic field around, it will start actuating. Part longevity is one of the benefits that we discovered completely accidentally. Is a lot of time, especially clear resins, they will start aging and yellowing with time. So here's example of jetted rubbery components that I was showing for PolyJet results. Those specimens are 4 years old. This is flexible clear. This is the same resin that is modified with carbon nanotubes. It stopped bending. It doesn't bend the same way anymore because specimens start aging and just loses its flexibility compared to carbon nanotube specimen that is still flexible, which is quite amazing. I'm taking them next week on a conference because we like to show that to people. The Formula One, how it became a product. Suddenly, when we were fabricating impact bars and decided just to put a resistivity meter on it, we discovered that our specimens actually conductive, which is not surprise. Carbon nanotubes have really high conductivity, but we use very low loadings. We were not really expecting that. So we fabricated surface resistivity specimens on a Formlabs machines on a black settings. Nothing is tuned to the best performance. And we measured surface resistivity at different loadings of carbon nanotubes. We went from anti-static region for the loading A, which is 10 to the 11, to static dissipative region, which is typically 10 to the 5, 10 to the 9. What is impressive about it, there is not a single static dissipative resin on the market. And why it's important? It's for electronics industry and for defense, where you have to protect your electronic components from electrostatic discharge. With all the electronic components becoming smaller in size, any spark can actually damage your chip, your memory, your processor, anything. It's just gonna fry it, so-called. So everything in electronics manufacturing production floor, on every stage, everything has to dissipate that electricity to avoid the damage to the components that are made. What is exciting in this, it's a VAT photopolymerization, which means properties do not change depending on the orientation of your part. Unlike in fused filament fabrication, Z direction is typically a problem, and it is a problem for conducting electricity as well. Here's the part we fabricated on VAT photopolymerization machine, and it's conductive 10 to the 5. And it doesn't matter which side we are measuring, our surface resistivity or conductivity stays exactly the same. If you would take a part fabricated using fused filament fabrication, you would get different reading, especially in the Z direction. Okay, moving along. One of the problems that people have with carbon-filled composites for static dissipative performance is carbon trail. What it means, you can use your part like a chalk and just draw something on a whiteboard with it, because there is so much carbon in it that your hands are dirty, your parts are dirty, everything around you is dirty with the carbon trail. So we conducted very, very sophisticated experiment here on our ESD part. We took it and we started to draw with it on a piece of paper. It's very scientific. Don't tell anybody how it's done. It's going to be future ASTM standard for sure. We just drew it on a piece of paper and we don't see any carbon trail whatsoever. Yet part is static dissipative. All right. And I will conclude. Discrete carbon nanotubes show a promise to deliver previously unattainable mechanical performance. We demonstrated 50% increase in tensile strength, over 200 in toughness or impact resistance, huge improvement in tear resistance and fatigue life cycles. We also could add additional properties such as magnetic, conductive, and many, many others. We just can't think on everything or can't take on everything yet. So with that, I will open the floor, well, virtual floor, to any questions you might have. Thank you for your attention.
Thank you very much. Thank you. Very good overview of the carbon nanotubes. Questions from the audience, please put it in the chat box. And Ala, can you please look to see if you see any questions while I'm figuring out? There's a Q&A tab there too, but let me see over there. So I'm going to have a very general question, and you kind of touched on that. So from Nobel Prize to maybe tens of thousands of papers to perhaps billions of dollars of money on carbon nanotubes, right?
Yep.
So
a lot of money went there. Mm-hmm.
Yeah. So where do you see future going with the carbon nanotubes? Its sister, basically material graphene, picked up the same kind of trend. The movement then died down. So where do you see really these applications? And I've been seeing some startup companies in different places basically trying to really get to the commercial side. From your perspective, where we're going to be in like 10 years with that?
Oof, that is a toughy one. That's a very toughy one. As I mentioned, in 30 years, we haven't seen anything so fascinating and exciting from the carbon nanotube world. However, I think more and more people started to actually realize what the problem is. That they tangled, they agglomerated, and you have to keep them apart. I truly believe we are not the only company that's trying to separate them and actually harness the potential of tubes. But I can tell you in 10 years, I don't think it's going to be space elevator or bulletproof vest. But we might see more and more carbon nanotubes in a composite, specifically substituting carbon fibers or carbon black. Again, as I mentioned, those materials, while they add properties, especially carbon black, it's typically used for electrical conductivity. But the loadings of that material in any composite is so high as 5, 10, 50% to reach the conductivity that is required for composite, which makes it detrimental in terms of mechanical performance. So it limits the application field right away. So with more and more progress in research, there is a lot of massive amount of research that done at universities for dispersion and stability of dispersion of carbon nanotubes. And I think, I think people shouldn't give up. Some people give up. Oh, there is no funding anymore. Nobody is interested. But, I think we're moving to the point that scientific community and R&D community understand what the issue is. And if we focus on solving those entanglement issues, we can see many, many applications in composite and replacing carbon black and carbon fiber. Graphene is a little bit different, but graphene, just like any other nanomaterial, has its own issues as well. No elevator, though. No elevator. Not in 10 years, okay?
Sure, yes. I guess we got questions from the audience. Pete Rocco is saying, thank you for your excellent presentation. Have you ever worked with nickel titanium oxygen nanotubes before? I'm a PhD student here at UT and working on shape memory alloys material. Just curious about basically what this.
Not directly. But we did have interest while I was at Open Additive, laser powder bed fusion hardware manufacturing. I was leading applications development. There was a lot of interest in printing that alloy for the shape memory devices, specifically for the medical industry. But I didn't work on it directly. It was, as we call it in industry, it was a lead, might be a project. It never happened.
All right, thank you. Nate Bender is asking a very interesting, a comment. Could you explain how you manufacture something like this box that was shown? Was it a coating or the structure that was basically mecnano product, basically?
This guy? Are we talking about this box?
I guess, Nate, you can confirm that?
Yes, he's saying yes. He's saying
okay,
in chat,
yes. Okay, thank you.
Yes, so this is PCB enclosure where you can put your any PCB, memory, whatever, electronic device into protective ESD covering. This is not a coating. This is done with our first product line, which we call Formula One, which is static dissipative resin for VAT photopolymerization. So we printed those specimens on a Formlabs Forms 3 SLA machines, and yep, no coating. I hope it answers the question.
Thank you. Thank you. Yes. So I have basically, and I see questions are coming, and basically we'll basically go through that. I just wanted to basically have this question on behalf of our curious grad students, basically. So you've worked in different segments. You've been in the university. Now you're basically working in a startup. So what are the benefits? What are the pros and cons of working in type of basically company that you're currently working? The size is smaller. There's not much that kind of organization. So I'm basically asking that question in case our grad students basically consider pursuing that career path versus, for example, you could have gone and worked with, Intel, with Applied Materials, with
the big boys, big boys, yeah. That's a good question. My entire career was in small businesses. 3 companies I worked with were all small businesses. Open Additive was part of UTC, but then span out in a startup. So McNano technically is a second startup for me. What I like in a startup, a small business environment, really flexibility. Startups typically work on something new, something cool, something exciting. Not like Intel doesn't, if there are Intel people in the audience. But, some absolutely new technologies, something groundbreaking stuff. Typically, sometimes it doesn't work. Startup is always a risk. So when I moved from Ohio, I lived in Dayton, Ohio, to McNano. I moved across the country with my family and my 2 dogs. And it's a huge risk when you make such a career move, because you don't know whether company is going to survive or not. You don't know if company is going to be successful or not, which requires from anybody. Well, for me, it's a lot of pressure. I'm director of technology. I have to push stuff out, right? But any level resource in a company like that is under a lot of pressure to deliver it fast and deliver good products, right? While sometimes you look at the larger companies, more established, it feels like it's more relaxed. However, at the end of the day, there is a cherry on top of the cake. Especially when you start. When I started, I was number 3 employer here. And you just look how your company progresses, how it grows, and you just feel proud that you were part of that. And it just a lot of flexibility. It's probably really bad thing to say, less bureaucracy than in the larger companies. You don't have to jump through the hoops to get something ordered. Like in some companies, you have to wait for those, things. It's for any graduate student that considers, one versus another, I would recommend talking to people that work in a different environments, or, somebody from the large company, somebody from the small business. Talk to them, get the opinion, what is best, weigh pros and cons, because as I said, there is a lot of risk joining the startup. There is a lot of pressure. But if you strive in that kind of environment, that's the perfect place for you. And then again, when it grows, you're just proud of all your achievements, and not only your own, but as a whole team, because your team is so small that teamwork is really important. Some people I know worked at large chemical companies for 3-4 years, and they didn't know half of the people on the same floor. Like, we know our entire team and very well, because we're 8-people company. So that teamwork becomes really, really important, that relying on each other and, trusting each other with different tasks and what we do, responsibility becomes a huge factor in the success of the entire company. I hope I didn't go too long with those explanations.
No, perfect. I'm hearing flexibility, stability, risk factor, and impact, all basically in different components in the trade-off. Thank you.
Yeah, absolutely.
And if you guys have any other follow-up questions related to that, please say. I have a question from Anwar, and sorry, Allah, I know you've been quiet, so
No, it's okay. I have been waiting. Okay, I can ask this question. So, nice presentation. What are the common methods for improving the compatibility of carbon nanotubes? Sometimes it's difficult to well incorporate it into other materials.
So that is what we do in terms of surface chemistry functionalization. That's the slide I was showing back, million slides back. Let me get there. Almost there. Here we go. So that is the most common approach, and that's exactly what we're using. It's oxidize the tubes, get reactive groups on top of on the side walls, and then the functional agent, or really the other functional group, you add in later on to optimize the surface chemistry. So you have to keep in mind that I cannot disclose the proprietary stuff. So this is all not proprietary. You can find it in literature. We have obviously our own tips and tricks, but in a sense, that's all you need to do. But you have to understand how your final chemistry on the surface of the carbon nanotube is going to interact with the matrix material of your interest, whether it's water, whether it's some solvent, IPA, ethanol, whatever you dispersing it in, or maybe it's acrylic or polybutadiene resin. So you have to, it's really, put it in a layman words, it's like dissolves in like, right? If you put oil to water, it doesn't like each other, it's not going to dissolve, right? look at it this way. You put carbon nanotubes that not functionalized properly in water, it's not going to disperse, it's not going to be stable, right? But if you functionalize them properly and match the Hansen solubility parameters, you can Google them. There is a lot of theories out there, but it's typically like dissolves in like. So you have to match that surface functionalization to the material of interest. And that is the most common, and you can find it in the literature. It's, again, it's a massive amount of research that's done on that front. Next.
So I have another question.
Sure.
Comparing to the mass production, so let's assume that we want to produce the carbon nanotubes with additive manufacturing and make this like, you know, a product. How fast, or basically the production rate comparing to regular, you know, like we know that it will improve the tensile strength, all the mechanical properties, but will also the time, the production time increase or decrease or stay the same?
In terms of when we process carbon nanotube composite additively versus
Yes.
versus resin not modified, okay. Let's put it this way. Carbon nanotubes absorb a lot of energy, thermal energy specifically. So if you think about laser sintering process, you modify your powder with carbon nanotube, what is going to happen when it absorbs more energy? You have to lace for shorter period of time, right? It's going to take less energy for you to melt that material, all right? In terms of VAT photopolymerization, it was a very interesting experience for us because first time we put the tubes in the resin, we put it in the 3D system SLA machine, small version of it, and zapped it with the laser. It's a SLA. What happened? Tubes absorbed so much heat, it boiled out the resin. It just boiled it out. There's no parts. There's no printing. You're done. So when we introduced carbon nanotubes in the next VAT photopolymerization project, we modified them and we called them low energy tubes for VAT photopolymerization methods specifically that do not absorb so much energy. But when we process them, it's really, here's the best probably example, tubes versus no tubes. We can print our carbon nanotube modified resin on a Formlabs machine on a black settings. So we are not adjusted settings. So if you take black resin from Formlabs, you're going to print exactly the same amount of time.
Mm-hmm. Thank you.
Mm-hmm.
Thank you very much. Let me see, Ala, do you see other questions or comments?
No, in the chat, no. And then in the Q&A, let's see, Q&A. No.
Okay. All right. Well, thank you. Very good presentation.
Thank you.
Good to basically learn some of the things, the new things happening with the CNT and all this forward. I appreciate this very to the point presentation. Ala, any last minute comments?
No, I would like to thank Olga really because she also had a commitment. So she did her best of making it for the seminar. So I really appreciate that. Thank you so much for joining us. And we'd really love to see more women in advanced manufacturing and manufacturing in general. So this is a great thing for us having you. So thank you for your time.
Thank you for the invitation. I enjoyed it.
Indeed. Yeah. Okay. Yeah. Thank you. Okay. We can conclude here. Thanks everyone. Have a wonderful afternoon. And I guess you're gonna have another hour, right? To get there. Still morning. Have a good morning for you.
Yeah, it's just around 11. I'm good. It's
Right.
lunchtime.
Okay.
Let's get in there.
All right. Perfect. Thank you. Thank you. Have a wonderful
Thank
evening.
you. You too.
Bye.
Bye-bye.
Bye.